Okay, hello Math 165 students. As I've mentioned, we'll be turning our attention to online learning for the time being. I'll be creating several YouTube videos going over these notes that I have posted to Blackboard, and so let's get right to it. Where we had left off, we had finished talking about exponential functions in class, and so 5.4 and 5.5 are all about logarithmic functions. And I've combined those two sections because the topic is pretty much just logarithmic functions. We talked about exponential functions, like I said, in 5.3. An exponential is a function of the form y equal a to the x, and an exponential is a one-to-one function. One-to-one just means that the inverse is a function, and when we calculate an inverse, it is all about switching x and y. Okay, so when I switch x and y in this equation, I end up getting x equals a to the y power. And sorry, some of that got cut off there. A to the y power. And now this function, x equal a to the y power, is so important in math that we give it a special name. We call it the logarithmic function. So here's a more formal definition. The logarithmic function to the base a, where a is a positive number, a cannot be 1, is denoted by y equal log base a of x, and is defined by y equal log base a of x if and only if x equal a to the y. Okay, a couple things. First of all, if and only if is a phrase that sometimes comes up in various math classes. All we mean by that is that we have two if-then statements. So one way that I could read this definition is beginning to end, how I would normally read it. I could also read it end to beginning, and I would have something that would be true. So in other words, if y equal log base a of x, then x equal a to the y. Also, I could read this as if x equal a to the y, then y equal log base a of x. So I'm going both ways with that. Both result in true statements. Now, like any other function, there's input values and output values. X is the input, y is the output, a is the base. The domain of the logarithmic function is all positive numbers. The base also has to be a positive. So, for example, suppose that I were to let the base be 2, and I'm choosing specific numbers here. Suppose that x is 8 and y is 3. Then 3 equals log base 2 of 8 can be written in an exponential form here. X is 8, a is 2, and y is 3, and so you'd be saying that 2 cubed equals 8. Okay, 2 cubed equals 8, that's a true statement. But if you write it this way in the logarithmic form, you're still saying the same thing. Okay, it's just a notational deal, it's how you're writing it. In this problem here, this example, I am having us sketch the graph of y equal log base 2 of x. And to do that, we would want to first graph y equal 2 to the x. Now, y equal 2 to the x is a graph that we already drew in section 5.3. And here's a table that we had used back in that previous section. I've got that same table set up here, and I've drawn that curve. This is the exponential curve, y equal 2 to the x. Of course, there's always a horizontal asymptote on an exponential. Now, I mentioned that an exponential is a one-to-one function. That's the first thing I mentioned. What does that mean? That means that the inverse is a function. What do we mean by inverse? It means that we're just switching x and y. Okay, so if I switch x and y in this equation here, I'll have x equal 2 to the y. Now, x equal 2 to the y means y equal log base 2 of x. So if I want to graph y equal log base 2 of x, I would have to graph the inverse function of y equal 2 to the x. Well, when you hear the word inverse, it's all about switching x and y. So that's all we have to do here in this graph. We need to switch the x and y coordinates on the exponential curve in order to build this logarithmic curve. Let me do that now. Okay, so negative 3 1/8, that's this point here. That's now going to be at 1/8 negative 3. Here's negative 2 1/4. That's now going to be at 1/4 negative 2. Negative 1 1/2 would be at 1/2 negative 1. 0 1 is now going to be at 1 0. 1 2 is now going to be at 2 1. 2 4 is now going to be at 4 2, and 3 8 is now going to be at 8 3. Also, this horizontal asymptote is going to become a vertical asymptote. Okay, so the curve is going to be kind of to the right of the vertical asymptote here, pulling away from that slightly, and it's going to pass through the x-axis at 1 0. After it crosses there, it's going to curl upward and outward towards the right into quadrant 1. Okay, so that would be just a quick sketch of the graph of this logarithm. I've also got the line y equal x drawn. So one of the things that we had learned when we talked about inverse functions is that a function and its inverse are always going to be symmetric about the line y equal x. That will always happen. Which means that one way to see how we got the graph of this logarithm is we just simply took this exponential and we rotated it about that diagonal line, and all the points will land in the same spot that you see I've got them plotted here. At this point, I want us to make some connections with the flow of the chapter. Okay, I mentioned at the beginning that the flow of the chapter would be kind of unusual. We talked about function operations. Specifically, function composition was in 5.1. We had to know that because in 5.2, in order to check if two functions are inverses of each other, you check through function composition. Well, a logarithm is the inverse of an exponential. In this problem, y equal to log base 2 of x is the inverse of y equal 2 to the x. So in order to talk about logarithms, obviously you have to know what an exponential is, and you also have to know what an inverse is. So those sections that were before this one here, or these two, are really just kind of preliminary information for being able to dig into logarithms. Okay. The domain of a logarithm is all positive numbers, or a basic logarithm, so you can see that on this graph. X can't be 0. I've got a vertical asymptote there, and a vertical asymptote is a feature of a logarithmic curve, just like a horizontal asymptote is a feature of an exponential curve. X negative won't apply either, since I don't have any graph on the left side of the y-axis talking about this logarithm. Now, if you want to graph any logarithmic equation, the plan is going to be similar to what we see here. You're going to have to first know the corresponding exponential, and then flip the coordinates, and you'll be able to get the graph of the logarithm. So like if I want to graph y equal log base 5 of x, I would have to first know the graph of y equal 5 to the x, since y equal 5 to the x is the inverse of y equal log base 5 to the x. Flip all the coordinates, and now I've got the graph of the logarithm. Okay. Now, one of the things that I always tell my algebra students is that it is super important that we memorize this definition. So many calculations that we do with logarithms just revolve around this one definition here. If you don't know that, that's going to be a problem for several things related to logarithms, calculations and such. So the next couple of examples that I have here are just where we're simply using this definition, and let's take a look at like this one. I have some exponential equations. I want us to rewrite the equation into a logarithmic form. Okay, so in other words, we are currently in the form x equal a to the y. We want to rewrite this into the form y equal log base a of x. So all we have to do is identify what is x, what is y, what is a, and then write it in the form y equal log base a of x. In part A, it looks like x is m, so that's going to be the input on my logarithm here. 1.2 is the base, that'll be the base of the logarithm. 3 is the y value, since that's the power, And so 3 equals log base 1.2 of m. That'd be my equation, but now rewritten into a logarithmic form. Part B, same deal. Okay, it looks like x is 9. The base is base e. Y is t. And so y equal log base a of x means that t equals log base e of 9. In part C, it looks like the base is 5. 2x is the exponent, so that'd be my y value here. And 13 is the x value, so that'd be the number going to go inside the logarithm. Now, we're not solving for x or anything like that. We're just simply rewriting one form into another form. Okay? In this next example, we're going the other way. So I've got some logarithmic equations, and I want us to rewrite them into an exponential form. Again, all I'm doing is I'm identifying what is x, what is y, and what is a, and I'm writing the equation in the form x equal a to the y. So right now I'm in the form y equal log base a of x. X for this problem is 24, so that's going to be all alone on the exponential. A is the base, 4 is the y value, so a to the 4th equal 24 would be my equation, but now rewritten into the exponential form. Part B, we have a base of 3, and y is negative 3. So that's going to be the exponent on the base e. X is t. X equal a to the y means that t equals e to the negative 3rd. And in part C, okay, x plus 7, that's my input here. So that's going to be all alone on the exponential. 3 is the base, 5 is the y value, which means that 3 to the 5th would be on the right side of the exponential. Again, we're not solving for x or anything like that. Okay. The next thing that we'd want to know how to do is to find values of logarithms. We'll do some more of this later when we talk about our properties of logarithms, but in these problems here, I'm just simply using the definition of a log. So y equal log base a of x means that x equal a to the y. Now, the idea with these problems is that I'm doing the calculations without a calculator. Part D, I could use a calculator, and I'll comment on that once I get there. To find the values of these logarithms, one option that you could do is you could call the expression y and then apply the definition. Right now we're in logarithmic form. If we rewrite this into an exponential form, x is 32, 2 is the base, and y would be the power of 2. So 2 to the y equal 32. Okay, now I'm in exponential form. And I'm solving for y, right? Because y represents this logarithm. If I find that number, then I'm done, because I'll know the value of log base 2 of 32. Being an exponential form, I want to get the same base. I can do that here, base 2. 2 to the 5th is the same as 32, so if I replace 32 with 2 to the 5th, then remove the 2's, it looks like y is 5. Log base 2 of 32, that's equal to 5 then. These other ones are going to be similar here, so I want to find the value of log base 3 of 1/27. Okay, I'll call that y, and I got to find the actual number for y. In this equation here, I'll apply the definition to rewrite this into exponential form. 3 is the base, y would be the power of 3, 1/27 is my x value, that's going to be alone on the other side. And I can get the same base here, I just got to think 3 to what power would give me 1/27. Well, 3 to the negative 3rd is the same as 1/3 cubed, or 1/27. So if I replace 1/27 with 3 to the negative 3rd and then remove the 3's, it looks like y is negative 3. Now here's something that I'd like you to notice. Notice how I mentioned earlier that the domain of a logarithmic function is all positive numbers. That does not mean that we can have a negative coming out of the calculation. That will sometimes happen. Okay, y is the output, right? In fact, if I were to go back to this problem with y equal log base 2 of x, if x was a number between 0 and 1, y is going to be a negative. Okay? So be sure that you know that a negative can sometimes come out of the calculation. Part C, I want to find the value of y equal log base the square root of 2 of 4. Apply the definition here. 4 equals root 2 to the y would be the equation rewritten into an exponential form. The square root of 2 squared would be 2. So the square root of 2 to the 4th would be 4. And again, I'm trying to get the same base here so that I can remove the bases and set the power as equal. Y equals 4. Okay, so log base the square root of 2 of 4, that's equal to 4. Part D, you'll notice that I don't have a base written. Whenever that is the case, the base is understood to be base 10. You can write the 10 if you want or not. Usually we don't write base 10. Knowing that, I want to find the value of y equals log base 10 of 0.01. Rewrite that into an exponential form. Again, the base is 10. Y would be the power of 10. 0.01 is the same as 1 over 100, so that'd be on the other side there. And 10 to the negative second power, the same as 1 over 10 squared, or 1 over 100. Again, I'm trying to get the same base here, base 10. I've got that now, and so I can remove the 10s and set the power as equal, so y is equal to negative 2. Now, I could have used my calculator in part D because most calculators have a log button on it. When you hit the log button, of course, you're working with base 10. There isn't like a log base 2 button and a log base 3 button and that, but there is a log base 10 button typically on most calculators. I suppose I could have used the calculator here, but I really didn't need to. Okay, I'll go ahead and stop here in the notes.